build AGI systems within a feasible time frame using the resources that we actually have available. However, I'm also interested to speculate, like many others, about what kind of AGI architecture could you build if you had insanely much computational resources. And this talk is more in that vein. So this is much more speculative than my work on OpenCog, because OpenCog is a system that I think we could use to get human-level intelligence.
I was thinking last night of hooking up some of this stuff.
In the near term, using computational resources now available. And we've tried to architect OpenCog so that we think the OpenCog system, once it reached human-level intelligence, is not going to annihilate everybody. I mean, we've taken specific architectural steps with that in mind. I mean, OpenCog has explicit top-level goals, much more so than, say, the human brain does, and it uses explicit probabilistic reasoning to help achieve these goals, along with other sub-symbolic dynamics. So we've tried to make OpenCog in a way that will make it predictably continue to work toward the goals that you initially gave it. And we think that if you take a young OpenCog and raise it nicely and supply it with intuitively plausible goal content, you'll get an adult OpenCog system that is reasonably in the vicinity of commonsensical human ethics. And all this, however, is quite intuitive, and there's nothing resembling a proof that if you have an OpenCog system with reasonable goal content and raise it in a reasonably nice way, it will be good according to the very vague human standard of goodness. It's also interesting to think about how might you make an architecture about which something stronger could be said. And the issue that I was thinking about here was, how do you make a system that could reprogram itself so that the AGI system can modify its own code, not in a trivial way, but in a reasonably fundamental way, to make itself think in fundamentally better ways. But yet, even though it can reprogram itself, it maintains basically the same high-level goals that it started with. How would you make an architecture that could do that? Of course, an architecture with this property would not guarantee you had a friendly AI in the real world, because we don't understand the real world very well at all. I mean, not only is our understanding of physics incomplete, I mean, our current assemblage of physics theories are logically inconsistent with each other at the moment, but there's all kinds of unknowns that could be there in the universe. I mean, there may be aliens out there, like living in the center of Pluto, and they're waiting for someone on Earth to get an IQ of 1,763. Once that happens, they're going to come to Earth and say, hey, welcome to the Smart Minds Club, right? And then, who knows what happens, right? They may reprogram our brains to make us evil killers. It may be utopia. Maybe they may give us a ticket to the better universe next door. I mean, of course, that's a fanciful example, but the point is there may be many unknown things about the universe that will be discovered by a mind that gets smarter. A smarter mind could discover a new physical force we don't know about and do all kinds of strange things. So, given that we don't know much about the world, there's no way you're going to come up with anything resembling a guarantee of what an advanced AI system is going to do. However, it could be possible to still prove something interesting about advanced AGI systems and to solve some of the tricky problems about things like goal preservation and self-improvement, which could give interesting information about AGI systems, even if nothing like a guarantee of friendliness. So I'm not going to give any formal proofs here, and I haven't worked out formal proofs about this, but I'm going to give what I believe are plausible arguments about a fairly simple architecture that may be capable to combine theoretical self-improvement with goal preservation. Now, the gotcha is this argument would require, at the moment, infeasibly much computing power, unlike something like OpenCog. Well, I'm not sure it requires as infeasibly much computing power as something like AXI, or these things that are just based on brute force, complete enumeration of program space. So it's kind of an open question how close you could come to an architecture like the one I'm going to describe within feasible amounts of computing power. So the goal of the speculative train of thought I'm going to pursue here is a system that is very generally intelligent, much more so than people. And I've done some work to mathematically formalize what I mean by that in a paper from the AGI 10 conference. I'm not going to go into that now. Reasonably likely to be beneficial to humans, dolphins, bunnies, other AIs, and all the other sentient beings out there. Pretty unlikely to be horribly destructive for, like, kill us all or, say, go nuts and put us all forever in a simulated version of the Christian hell or anything else that you could think of.
That's all
I'm going to assume that the way we get to this massively superintelligent system is to create a system capable of radically self-improving. I mean, that's not necessarily the only way. I mean, you could make a cellular automaton that somehow crystallized into a superintelligence without using intelligent processes. But I think it's a pretty likely way of doing it. Basically, you make a human-level AI, you teach it computer science, you teach it computer programming, and then you teach it how it was built, and you say, well, can you do better than this crap? And then it revises itself and improves itself. And I think that's the most plausible path to get to a massively superhumanly intelligent system. I'm then going to define a slightly new concept. I'm going to define a system as being steadfast if it's not able to give up its initial goals. And if it sees a great threat of it giving up its initial goals, right, it just stops doing anything. Either it kills itself or just stops acting. So, and this way of thinking is necessary because, I mean, given the uncertainty about the world, it's hard for a system to guarantee it's always going to be acting in pursuit of its goals. Depending on what the goals are, it might not be possible. So it seems it's easier to argue things about this kind of steadfastness than about always in any circumstance pursuing your goals. Now, you can make various tricky arguments about it, like what if it tricks itself and only pretends to itself to pursue its goals until a certain point and then annihilates itself. But I don't think those are really problems when you think through them carefully. So the questions I'm going to briefly pursue here: how would you create a massively supremely intelligent, self-modifying, steadfast AI system, one that will keep pursuing its goals, and if it can't, just stop doing anything? And you know, what way of defining? All right, yeah, that's a bit of a mistake. Oops. The top there was supposed to say how to create a massively, superhumanly intelligent, self-modifying, steadfast AGI system whose goal system includes being beneficial to us. So let's hope we don't leave that out when we create the actual. How would you define beneficial to actually make that work? Because that's another problem. I mean, even if you had a system that would guaranteeably pursue its goals in a steadfast way, I mean, how well do we have to specify the goals? I mean, if you have to specify the goals in like predicate logic format, you're kind of screwed because we don't know, and we'll probably never know, how to specify like common sense human morality in predicate logic. But if you could specify the goals by a combination of natural language and a bunch of examples, if that way of specifying the goal, which is how we specify ethics to each other, if that was good enough in this context, then we're in a better off situation. So it's a quite simple architecture. I made up a peculiar analogy, acronym, but it's a goal-oriented learning meta architecture, or the Golem, going back to the original AIs made of clay by the rabbis in the 1400s. So then the basic idea of the hypothetical future Golem is, so there's an operating program that basically runs the system. It keeps doing stuff. And then there's a meta program whose goal is to update the operating program. And it might never do anything, but if the system's going to get smarter and smarter, the meta program is handling the rewriting of the operating program. And then how does it rewrite the operating program? Well, it doesn't do that willy-nilly. It rewrites the operating program specifically in ways that it thinks will help it achieve its goals better. And the goals are basically described as mathematical functions defined over the future history of the system and the world, including the system's internal state. So it's not strictly a reinforcement learning system. It's not trying to maximize some average expected discounted reward or something. You can give it any kind of mathematical goal function over the future of itself and its environment. And then, so the meta program asks basically, okay, I will search the space of possible operating programs by some algorithm. I will try to predict what each candidate operating program would do. How well would it, based on my history, how well would it help achieve the goals? And then if I arrive at an operating program that I believe will rationally help me achieve my goals better, based on my history, I will put that operating program in place. And if I can't do that, then I won't change the operating program. Now, so this does not allow total rewriting of everything, right? So there's some low-level control code that manages the process of testing new possible operating programs. And that low-level control code, you have to assume, is not going to be revised. It has to be part of the goal system. But yet you can still achieve arbitrarily high levels of Kolmogorov complexity in the operating program, depending on the complexity of the environment. I mean, there's a limitation to how fast the intelligence of a system could possibly increase if it's just optimizing itself in a vacuum. You can't increase faster than logarithmically or something. But if you're embedded in a very complex world, which has vastly higher algorithmic information than you do as an individual system, then you could see the algorithmic information of your operating program increase quite rapidly as you learn how to achieve your goals better, because there's so much new information coming into the historical repository from what's happening in the world. So to review a little more carefully, I mean, the goal evaluator calculates for each possible future world how well the world will fulfill your goal. And the possible future world is one that may result from some actions that you take. Historical repository just stores past history of your internal states and your actions. The operating program is what governs your actions. The searcher searches through program space. The memory manager is a program that decides what to put into the historical repository and what to delete from the historical repository if you run out of memory, as will happen with a finite system. The tester is a component that uses historical backtesting to figure out how well a predictor works. Because you want to be able to optimize your prediction algorithm as well as your operating program. So every part of the system can be optimized. I mean, the way you search can be optimized, the way you can predict can be optimized. The only thing you can't let to really be optimized is how you evaluate your goal. Because if you let the system optimize how it evaluates its goal, of course, it can just pathologically hack its goal evaluation function to be something totally different. And that's a bit of a limitation. Now, if you want to make a system like this somewhat conservative, you would make a goal where the goal includes some clauses like this. I can't change my low-level control code. I can't revise my hardware. That's got to be constant. And if changes are made, then I should stop acting. So the only way it can rewire itself is to turn itself off, basically. And I mean, this is a significant limitation, and it's going to make it stupider than the system without this kind of goal. On the other hand, it can still become very, very, very smart in the sense of increasing algorithmic information. And I give in a paper I put online an argument as to why this system should be steadfast. Basically, I mean, if the goal evaluator and the environment have the property that, if the system preserves its architecture, that will mean it's achieving its goals. If the system is not preserving its architecture, that means it's not achieving its goals. If this is the case, you should be able to show that the meta architecture is very likely to be preserved. Because what's the system doing? It's trying to achieve its goals, and its goals include the goal of preserving its architecture. And the main problem with this approach, which is similar in spirit to Schmidhuber's Golem machine, but not identical when you dig into the details, because it's not a reinforcement learning system, for example, but it's similar in spirit. The conclusion you come to is if you built something like this, it would probably keep achieving the same goals it started out with. Now, this doesn't prevent you from invoking the aliens inside Pluto who notice that you did something and come and rewire your hardware, even though you wouldn't do it yourself. And of course, it will be inefficient, right? One way to make it smarter but less conservative, if you let it optimize its goal evaluation function, it will probably become smarter, because you look at, it's modifying every other part of its architecture, right? But it's not allowed to modify how it evaluates its goal function, because then it might cheat. But of course, then it's going to be 10 billion times smarter than us, but it's still going to be using this stupid goal evaluation methodology that we programmed it with, right? But you need some restriction like that to make it maintain its original goals. And of course, if it can't upgrade its hardware, then that's a very simplistic assumption. Now you could look at modifications that let it upgrade its hardware in ways that were provably okay, but there has to be some low-level control mechanism that you don't allow it to rewrite. Otherwise, I don't see how to do it. There might be a way to do it, but the only way I see to make something able to keep modifying its own code and maintain its goals is to have some core that can't be rewritten. And fine. So, how could you ever build something like this? Well, the first step would be to acquire amazingly massive computing power. It's not clear you would need an AXI. There may be search algorithms through program space that are much smarter than complete, just brute force enumeration of program space. But it's way beyond program search algorithms that we have right now. Could you do this by extending some existing AGI system? I don't know. It's clearly harder than just making a human level AGI though. So it's unlikely to me that an architecture like this would come about before a human level AGI with fewer safety mechanisms, just because this would require many more computing resources and be much more difficult to do. Something like OpenCog, even if you put it as the initial operating program, you'd need to have something able to search the space of programs like OpenCog and find better and better programs like OpenCog. And I think that's a harder problem than making an OpenCog in the first place. Another huge open question is how would you define beneficialness? And if you can make a mathematical definition of it, that's one thing. But I'm not sure that's possible to do in a meaningful way. So then you would have to tell it, okay, define beneficialness kind of like by analogy to these examples and interpret these examples kind of the way a human would, but it becomes quite difficult. And this, I think, is what I would like to get out of the philosophy community associated with the future of humanity and the study of AGI. If the philosophy community came up with a good solution to the problem of reasonably formalizing, what is the ethical goal in the first place, that would certainly be quite interesting. And it may not be, I don't think it's going to be a logical definition of what good is. It could be a formalization of the procedure for estimating what's good based on consulting humans and watching humans or something. But somehow addressing the problem of what is the goal seems like a thing that philosophy should be good at, and computer science definitely is not well equipped to solve, right? And there's various ideas out there. You can let everyone vote on one. That works out really well in politics, right? You can. Eliezer Yudkowsky had the idea of coherent extrapolated volition, which is like quite speculative. Basically, it's try to extrapolate what everyone would want if everyone was the person that they wanted to be, which is not tremendously well defined, really. So there's a lot of difficult open questions here, and it may be that this line of thinking is too far removed from reality to amount to anything, but it's interesting to reflect on the difference between this kind of architecture and something like OpenCog, and on how much more difficult it is to build something like this than to build something like OpenCog. Making a system that can really modify itself in a way that is, if not guaranteed, at least very unlikely to change its initial goals, requires you to be able to intelligently evaluate various alternatives of the level of complexity of the original system, right? And that's a harder problem than the system usually has to solve in its ordinary life. I mean, take what we humans have to do in our ordinary lives, right? We very rarely have to do something as hard as create and evaluate an ensemble of different human-level AI systems of different types and figure out how good each one is going to be. Like that's a really hard problem compared to getting sex or getting food or even compared to programming an AI system. So it's in the most naive way to pose it, it's a quite difficult problem. And so that one question is whether it's even possible to make a system that fulfills the specifications that Golem is supposed to fulfill to enable both goal preservation and radical self-improvement. I mean, that's one interesting question. And then the other question is, how could it possibly happen that this is the first kind of AGI to come about? Because I mean, let's say I got 90% of the way to making OpenCog and said, well, I don't want to do that because I'm afraid of what's going to happen. Instead, I'm going to wait until I've refined something like Golem better and made enough hardware to really do this. You know, some other guy is going to make something like OpenCog and make it into a human-level AI within a few years. While I'm sitting there figuring out how to do something that requires orders of magnitude more computing power and more complex algorithms. And how to avoid that problem is more of a sociology problem than a computer science problem. And I posited the speculative notion of an AGI nanny to solve that problem. Like create a human-level AI that doesn't want to self-improve, and its goal is to watch the world and make sure no one creates an AGI smarter than it, until someone figures out how to build a Golem or something like that, right? But of course, there's so many ways that kind of benevolent AGI dictator could go wrong, right? And science fiction and human history have explored that family of ideas pretty well. So I don't actually see any easy answers to any of these questions. I tend to be an optimist that we're going to create AGIs that are going to be beneficial if we build systems like OpenCog or other rationally grounded AGI architectures, give them goals that plausibly seem beneficial, and raise them and teach them well. That's what I think is going to happen. But I have to admit that's based more on a non-scientific sort of intuition than on grounded scientific reasoning. And there's time for a few questions, I guess.
Hi, Ben. So I'm assuming that your goal evaluation probably includes something like making sure that it hasn't changed its architecture in some way where it bypasses the goal evaluation. But how do you make sure
that's explicit.
So I guess you also have to include that Golem doesn't.
That's there. Yeah,
Golem doesn't
low-level control.
Yeah, and Golem doesn't build Golem 2 that doesn't have the goal evaluation in it. So you don't roboticize it and have it build another Golem that then removes that constraint. Right.
Yeah, that depends on what. That's just a matter of the intelligent definition of the goal function, right? So. Yeah, you would have to ensure that, but I don't think that's an obstacle.
Yeah, I mean, it could only be an obstacle if this becomes one of those never-ending things where you then have to guard against so many other possibilities. But, yeah.
I wasn't quite clear if you had a module that could reliably look at the program and see whether that program would be efficient at achieving high utility according to a given utility function. is obviously a difficult module to build, but if you had that, it's not clear why you would need this complicated architecture. Couldn't you just use that as both the meta program and the operating program, and it would select actions based on its predictions as to whether that action would realize its current utility function. And one possible type of action would be to modify itself in any arbitrary way. And if it were reliable at estimating the implications of such an action, where the action might be installed in this new program that will then guide me, then I don't see why you need this extra control loop there.
Well, I mean, the extra control loop is an initial architecture that does that, right? So what you're saying is, once you had found a better way to do this whole control loop, if you were really sure of that, you could just put that in place of your operating program, and then you know for sure that you're going to be doing the same thing as this anyway, right? I think that some form of that is probably true. I'm not sure that it doesn't make the problem any easier, right? I mean, that becomes more like the Goertzel machine if you do it like that. Except that the Goertzel machine is found on reinforcement learning, and this is trying to optimize some function over the future, rather than trying to maximize the expected reward.
Okay, Alan King is my name. I first want to make a quick statement to get something off my chest, and perhaps get half the people here mad at me, and then I have a real question. But my observation on a lot of this is that it's kind of like the Wright brothers, as they're looking at efficiencies of engines, trying to design their control mechanisms so that jet airplanes wouldn't fly into the World Trade Center and cause 9/11. It seems so far. It's way too hard to extrapolate. That's just a statement. With that off my chest, I look at your diagram there, and as you were describing it, I do all those things as I program. And so what's the difference, except for the fact that you've replaced me by a machine? How is this different than just a programmer programming the next version of AGI?
Well, actually, let me go back to it. Let me try to give a better answer to his question. Now, I'm going back to what I was thinking of initially when I made this up. So the reason why I wanted to start with this type of architecture was to deal with the early stages of learning, because we have the learning is going to be pretty approximate, right? I mean, you don't have infinite computing power, and you don't have that much experience, so you're not going to come up with some kind of highly certain conclusion that you have the right operating program to use. It is going to keep you stable and keep you preserving your goals. So my feeling was that if you have this sort of architecture wired in, which indeed you could just pat that all into the operating program, which would make it a smaller diagram. You could say that whole thing is your initial operating program, and then there's a sub-operating program whose job is to do everyday routine actions, and then there's the rest of it, which is more introspective and focused on revising your mind. But my feeling is that in the initial phases of learning, you will make fewer mistakes if you're required to preserve this type of architecture than if you use something like a pure Goertzel machine, where you can just revise yourself in any way based on what you think you have proved is correct. But this is more a matter of what is the profile of errors that you're going to make given limited resources, which is it's something I tried to prove things about and failed so far, actually. But given infinite resources, that doesn't matter. But given finite resources, the thing is going to make some stupid mistakes, and the question is which way of doing it gives you fewer stupid mistakes.
Yeah.
So
Are you going to answer my question?
How is this different than what people do?
Yeah.
Well, I mean, you could say people do these things, but just do them very badly. I mean, we don't do a very good job of searching all possible alternate ways of being that would achieve our goals, and then rewriting our mind state with a better way of being that would achieve our goals. And when writing software, I don't think we do a particularly good job of that either. I mean, I think our erroneousness when we go about doing that is sufficiently bad that I think we would diverge very widely from our initial goals.
So this involves exhaustive searches.
Not necessarily. That's the extreme case. The extreme case would be exhaustive search, and then something like OpenCog or a human being is at the other extreme, something that's not that smart, and it's not clear what lies in between. Actually, it's unknown how well or how badly you could do it this with different learning algorithms at different levels of complexity.
We have time for one more question.
Michael Buchanan. So, if you make OpenCog human level, it would have capacity to do software engineering, and that would have capacity to self-improve. So, it would seem that in the spirit of previous discussion, it should start with doing something like this badly and try to learn to, as it improves, to make it better. Basically, sort of. Is that the right road? Because you don't think that you will forbid OpenCog human
Well, the
based?
thing is, if you try to do something like this right now with the technologies we have, you would do it so badly that the system couldn't really do anything. It would just be doing some toy problem in some simple toy domain. So then on the one hand, you have a very simple toy self-modifying system, which is incredibly small and uninteresting except to theoreticians. And on the other hand, you would have a proto-AGI system that didn't have anything as close to a guarantee associated with it, but that could actually do stuff in the world, right? And there's a big gap between those two at the present time, because the problems that an AGI system has to solve in solving real problems in the world are much easier than the problem of optimizing systems of the same complexity as itself.
Right.
Thank you, Ben.